Hello again. This is another video on chapter 4. Most probably we are not going to be able to finish it, but see how much we can finish. Okay, I hope you're doing well. So let us get started. And the next section, of course, we want to talk about is section on applied optimization problems. It's similar to related rates, but in this case, we are working with one function we call objective function. So let's look at an example. Let's start with an example. So this is an example that we want to, says a rectangular garden is to be constructed using wire fencing for all sides. So all of these sides have to be wire fenced. Given 100 feet of wire fencing, determine the dimensions that would create a garden of maximum area. What is the maximum area? So see, the problem usually involves an objective function that needs to be optimized, right? So optimization involves either minimization or maximization. So either you maximize or minimize the objective function. That's what's called optimization problems. So in this case, what do we have to optimize is the area of this garden that we like to optimize. Now in this case, we want to maximize it, right? So we want to know if we are limited, if we have limited amount of fencing, with that amount of fencing, what kind of rectangular area should be enclosed? So it should be enclosed a rectangular area that is long this way and short the other way, or should we have just a square, or should we have, what kind of rectangle should we have to maximize the area of this garden with the same amount of fencing, which is 100 feet. So here we have 100 feet of fencing, and we know the parameter. So what we need here is variables. So we come up with variables. We have two. Of course, they're different because they're not necessarily the same. So this is a rectangle, it's not necessarily a square, right? So these are two different variables. So we got x and we got y. And the parameter of this would be 2x plus 2y, right? So that's the parameter right here. The area is x times y, which is that right there. Now, once we write these, we realize that it doesn't make sense to say maximize the area if we don't have any other information. Why? Because, well, if you want to maximize the area of a rectangle, just make x and y as big as possible, right? That doesn't make sense, right? So there are some constraints in our problem. There are limitations on x and y. What is the limitation in this case? Well, the limitation in this case is that the parameter is only 100 feet. So what do we do that? From the limitations that we are given, we're going to find a relationship between x and y, and then in our area equation, which is the one that we have to maximize. Well, you remember in calculus 1, we cannot maximize a function if it's a function of more than one variable. We do that in calculus 3, right? So what we have to do here, we have to make sure a is a function of one variable only. So how do we do that? Well, we have to replace one of the variables in terms of the other one. And this relationship between x and y here can give us that equation that we need. So we say 2x plus 2y has to be 100, or x plus y has to be 50, so y has to be 50 minus 1, minus x. So we're going to take this and substitute it here for y. And now a, which is the area, is actually a function of one variable only. And that's what we call objective function. So the objective function is just that. All right? Now, is there what is the domain? Now obviously the domain, this is a polynomial, so the domain is all real numbers. But that is the domain if we consider just the expression here. That's what this implies, right? But the actual domain in our problem, x cannot be any number, right? What values can x take? Well, if you take a really long rectangle this way, well, x could be close to 0. Can't be 0, because if x is 0, you don't have a rectangle. So x is between 0, and what's the maximum x can be? Well, the maximum x can be is 50, because that 50 plus 50 is 100, and then y should be 0, right? If x is, x and y are 50, then y has to be 0, right? So that means we don't have fencing for this sides. We only have for x, right? 50, 50 is 100. So x can't be 50, but it could be close to 50. Let's say if x is 49, then we have 2 feet left for the y, the two sides, so it would be one of each. So it would be a rectangle as 1 foot, and then it would be really long, right? All right, so x is between 0 and 50. Okay, now that we have the objective function, which is that right there, how do we maximize it? Well, that's easy, right? The domain that we have to maximize this on is from 0 to 50. And 0 to 50 are not included, so it's an open interval. So we're going to put it here in this table. The first row would be from 0 to 50. Now, from 0 to 50, what are the critical numbers of ax? We just take the derivative. Derivative is basically 50 minus 2x, right? Set it equal to 0, and that's our critical number. There is only one. So we put it here. Now that's all we need, really. We're not graphing a of x. We just want to find out between 0 and 50, what is the number that maximizes this function, right? So we take the a prime, and we know a prime is 0 at this point, so we put a prime here, and we put a here, just like we did before. So now a prime, we do a sign analysis for it. So at, let's say, pick a 20 number to the left of 25, let's say 24. We substitute here, here in a prime. Put a 24 here. 50 minus 2 times 24 is going to be a positive number. So that's positive, and it's negative here, right? So that means the function increases here, decreases here. That means the maximum happens at 25. So let x be 25, right? And we know the relationship between x and y. X plus y has to be 50. So if x is 25, y has to be 25. Right? So this is square. That is what? 25 by 25. That's what you should build. If you have only 100 feet of wire fencing, then to make an area, let's say you're given that much, right? And you're given land, free land. Say, okay, just enclose. Whatever you enclose is yours. Well, how would you enclose that land? You make a square, okay? So now you know. Next time you're given 100 feet of wire fencing, and has to just enclose an area is yours, that's what you do, right? So square maximizes this here. Oops. Right, so let's continue. So here I'm gonna show you the graph of a, which is the area function, and as we change make x values different, right? You're going to notice here that the maximum happens, you see. See, that's the area that we're going to get if we make different x values, right? Area increases, obviously, as you see. By the time we get to 25, area is maximum. If we pass 25, make x longer than 25, again, the area decreases. And we don't care after 50 what's going on, because after 50, there is no interest, right, for us. We are not interested in these numbers because we don't have, there is no way x can be greater than 50, right? So that's the idea. All right, so let's continue. So let's go over the steps again quickly, what we did here. So to do an optimization problem, to solve it, first thing you do is introduce all variables. And we did that in the previous problems, right? We did variable x and y and draw a figure, right? We drew a figure. Determine which quantity is to be maximized or minimized and for what range of values of the other variables. And we did that, of course. Area was the one that had to be maximized. The range of x values we figured out were 0 to 50. The other variable was y with the same range, right? All right. The third step, write a formula for the quantity to be maximized or minimized in terms of the variables, right? And we did that. So here we go. That's what we did. And then, of course, this formula may involve more than one variable, and it did in our example. And we also had the parameter given, which is the constraint, right? The limitations on the variables. Okay, and then write any equations relating the independent variables in the formula from step 3. And we did that already, right? We wrote the equations P and A. And then use this equation to write the quantity to maximize or minimize as a function of one variable. So we're going to use this to write this as a function of one variable, and we did that. All right, and then identify the domain, and we did that already. The domain was 0 to 50, right? And now we have what? Now we have we have to maximize the function actually. So locate the maximum or minimum depending on what we are asked to do. And we do that by basically finding critical numbers. Now if the interval we are given is a closed interval, right, is a closed, then we are going to do what? We're going to find the values at the endpoints as well. Now in our problem, it wasn't closed, so we didn't have to do that. So we just find the critical numbers and do sign analysis for the function derivative of the objective function, and we are done. All right, so let's do another one. It says, of all boxes with a square base and a volume of 100 cubic meter, which one has the minimum surface area? So here is a cube, and not cube, but rectangular prism, right? Is a box. The base is square, but the height could be any variable, right? So we have two variables, x and y. Now what is it that we want to optimize in this case? Surface area, right? Surface area has to be minimized. So we take our variables, which is x and y, write an equation that relates the variables. Now surface area, what's surface area? Well, surface area of this thing is the area of the bottom plus the area of the top. So the bottom is x squared, the top is x squared, and then we got this side, side behind this one, and the side to the left of this one on this side. So we got 1 x times y, x times y, x times y, and the one behind it is x times y. So we got 4 x times y's. So that is the surface area. So surface area is 2x squared plus 4xy. That's the surface area. Okay? Okay. All right, I'm back. Sorry about that. I was looking for the pen. All right, so this is the objective function. So we got that. And now the surface area is the objective function. Now, what is the constraint here? Because if somebody says, you know, minimize the surface area here, it doesn't make sense, because we say, okay, you want to minimize it, just don't build it, right? That would be minimum, would be 0. So we have to have constraint here, right? And the constraint here is the fact that we have what? Limited volume. So the volume, what is the volume of this thing? What is the volume of something like that, a rectangular prism? Well, we know the volume is the area of the base times the height. Area of the base is x squared times y. So volume is x squared times y. Now, is it limited? Yes. So volume has to be 100. All right, so we got this, and then we got this. That's what we have to work with. Now, we know that surface area has to be a function of one variable. We got two variables here, so one of them has to be replaced. Which one? Well, maybe y, right? So we're going to replace y. How do we replace y? Well, we're going to solve for y in this equation. Y is 100 over x squared. So we're going to take this and substitute it here for y. What do we get? Well, s is 2x squared plus 4x times y. And we simplify, we get this. We got our objective function. Now, what is the domain for our independent variable x? Well, in theory, x can be really, really small, close to 0. So we're going to have a really, really long rectangular prism. Or x could be really, really big. So we have a rectangular prism that is vast, but the height of it is really, really small. So in theory, x can be really, really large. It can't be infinity, but it could be really, really large, right? All right, so that means the domain is from 0 to infinity. It can't be 0, it can't be infinity, right? So we create our little, we take our derivative. What's the derivative of this thing? 4x plus 400 times 1 over x. Derivative of 1 over x is negative 1 over x squared, right? So this right here is actually 400 times 1 over x. So we keep the 400. What's derivative of 1 over x? Well, that's another derivative we can memorize. Derivative of 1 over something is negative 1 over something squared times something prime. You want to memorize that, or just write this as x to negative 1 and take the derivative of it, which is negative 1 times what? X to negative 1 minus 1 is negative 2, which goes in the denominator, becomes that. Okay, so that's the derivative. So we set it equal to 0. Obviously, there is one critical number at 0, but 0 is not in the domain, so we don't care about that. So what's another number that makes derivative 0? We set it equal to 0. We have a rational equation, right? We solve it. We move this to the other side and solve this. Multiply both sides by x squared. So x equals to cube root of 100. So that's the number that makes what? That makes the surface area minimum, and the volume stays at 100 cubic meter, right? Is this important in application problems? Yes. Let's say you want to build a box that has this volume, and it has to be rectangular, maybe for shipment purposes. It's rectangular is the best. So what kind of box would you build so you won't waste as much material to build it? You minimize the surface area. That means you minimize the materials that are used, right? So that is the answer. We can put the domain again on the top of this table, put this number here, do sign analysis for s prime. If you put a number smaller than that, this would be negative. And bigger, you can use a calculator if you want to find the signs. But it's negative here, positive here, so the function decreases here and increases after 0. So that means at this point, this function, where is that function? That function here has a minimum, right? So minimum occurs at about this number. So what is, if x is cube root of x, cube root of 100, if x is cube root of 100, what is y? Well, y is what? 100 divided by what? X to the second power. Now, cube root of 100 to the second power, right? But what is that? Well, cube root of 100, what's cube root of 100? Well, that's 100 to what power? To 2 over 3, right? That's what that is. And what is that? Well, that's 100 to the power of 1 minus 2/3, which is 1 over 3. Which is what? Cube root of 100. So that means x and a y both have to be what? Cube root of 100. That means you have to build a cube. That's the best rectangular prism to make, a cube. Okay, for what? To minimize the surface area. Okay, one more. And this one has to do with a problem with minimizing time. So it says an island is 2 miles due north of its closest point along a straight shoreline. So it's a straight shoreline. The closest is perpendicular to the shoreline, right? So that distance here is 2 miles. So it's 2 miles, right, due north of its closest point on the shoreline. So that's it right there, 2 miles. So a visitor is staying at a cabin on the shore that is 6 miles west of that point. So here you go. This is the point. Here's the cabin, 6 miles west of it. So this distance is 6 miles. A visitor is planning to go from the cabin to the island. Suppose that the visitor runs at a rate of 8 miles and swims at the rate of 3 miles. So this person can run this way, 8 miles per hour, can swim 3 miles per hour. Now the question is, should the person just swims all the way to the island, or should he or she should go run for a certain distance and then swim? How can the person minimize the time that it takes the person to get to the island? And that's not an obvious answer. There's no obvious answer here. So what do we have to do? We use calculus. So what is it to minimize here? The time that it takes the person to go from here to the island. Part of the way running and part of the way swimming, right? And of course, you don't want to pass this, right? Because obviously, if you pass this, you're increasing the distance. So really, you don't want to go past this, and we're going to see why in a second. But for now, x really, well, let's say what variables we have. So basically, this point changes. So this point could be here, right? And then go to the island, right? It could be here, and then go to the island. So this distance here is actually what is x. It could change, right? So we call that x. And then is there another variable that is changing? Yes, besides this one, this distance also is changing, which is y. So we call that y. So I'm going to erase the red one so we can concentrate on this just one. You can put this point anywhere, but we put it here for now. So the person has to go run x miles and then swim y miles, right? Now it could be the case that x turns out to be 0, so the person has to swim all the way. Or maybe y is going to be 0. That means y maybe is going to be the whole thing, right? And x could be 0. Or x could go all the way to 6 here and then go this way. We don't know. So let's see what we have here. So what is it that we have to minimize? We have to minimize the time. Now what's the connection between time, distance, and rate? Well, distance is rate times time. So if you go 40 miles per hour for 2 hours, well, you go 80 miles. You multiply them, right? Now in this case, we made it really easy because the rates are constant, right? The rate of running is constant, the rate of swimming is constant. So we have to isolate time from this relationship. So time is going to be distance over rate. So how long does it take the person to run from here to here? Well, what's the distance? Is x. What's the rate? Is 8. So we divide it. Right? So that would be t for this part of the way. And the other part of the way, how long does it take the person to swim this much? Well, it would be the distance, which is y, divided by rate, which is 3. So the total time would be the time that it takes to go this way and then that way. So we add them. Here we go. We got the objective function. Again, the objective function has 2 variables. So we have to get rid of one of them. How do we get rid of one of them? Well, we look over here and see if we can find a relationship between y and x. Well, notice that if this distance is x and this distance in here, this distance is 6, then this one here would be 6 minus x. And we have a right triangle here, and we know Pythagorean property. This squared plus this squared equals to that squared. And if we do that, 2 squared plus 6 minus x squared equals to y squared, we can solve for y. Y cannot be negative, so we don't put plus and minus, just put plus. And we put it in our objective function. This is it. This is our objective function, has to be minimized. So we are going to take the derivative of this. And, we did that already. So let's take, the x can be 0, right? X can be 0. If x is 0, that means y goes all the way from this point to that point. And x could be 6. That means you can come all the way over here and then swim, right? So x could be 6. And in a second, I'll talk about why x should not be more than 6. Now you could, run, go all the way to 100 and come back this way. But it doesn't make sense. In a second, I explain. Okay, so we need to minimize the objective function. So take the derivative, and we're done, right? Take the derivative of this is just 1/8. Derivative of this is the square root. So what's this? Derivative of square root of something. Well, first of all, this 3 and this 1, let's say there's a 1 here. We bring the 1/3 right here. What's the derivative of the square root of something? Remember, you have to memorize that. There's 1/2 square root of something times what? Something prime. So 1/2 square root of something times derivative of inside, which is that, right? You agree derivative of this is this. Derivative of 4 is 0. Derivative of something squared is 2 times something to the first times derivative of inside, which is -1. So we simplify, we get this. So we're going to set this equal to 0. So take this to the other side. What do we have? We have a equation that has radical in it, right? And we know how to solve it. Isolate the radical. So cross multiply and take square both sides. And simplify. This is just a little algebra. You multiply and simplify. And instead of expanding it, if you notice here, they have something in common. So we can group them, right? So it's 9 times 4 is 36. 9 times this is just 9 of these. And then we got 64 of these, right? This way we can move the 36 to one side, keep the 36 here and move these two to the other side. So move this one to the other side, keep the 36 here. And now we have 64 of something and 9 of something. We subtract, so 55 of something. And then that something we isolated because this is squared already. And we find out that this is squared equals to this. This is a really easy quadratic. Take square root of both sides. And finally we get x is 6 plus and minus this. So x is either 6 divided by square root of this plus 6, which is going to be that. And then 6 minus this, which is going to be this. I mean, this would be minus, this would be plus. So this one is not in the domain. And is an extraneous solution that we get. Is not in the domain, right? Because the derivative really is not defined at, at 6, because 6 makes the not defined as 6, but we set derivative equal to 0 to find these two numbers, right? So this is a number we're going to see in the graph in a second, what we do with this. But let's think of 5.19 in a second. So here we go. So the t of 0, right, which is the left endpoint, t of 6, which is the right endpoint, right? Remember we had 0 to 6. X could be any of these numbers. So we find the endpoints and we find the value of 5.9, right? Remember our domain was that. So the other one, 6 point something, is outside of this domain, so we don't want it. And so t of 0 is like 2 point something. You can substitute in the formula and see what you get, right, with the calculator. T of 6 is that. T of 5.9 turns out to be that one. And now I'm going to show you the animation of this thing. Right here. So let me, okay, here we go. So this is the point. You see I'm changing what? I'm changing x. And notice that when it becomes, horizontal, it's about right there, 5 point something that we found. It's about right there. You see this is the time. So time starts from here and goes all the way down to this point and goes up, right? As you see, right? So I didn't let it go past that because we don't really want to go past that, right? So basically you want to know how much you have to run and how much you have to swim, right, from here to here. That's the shortest distance, right, of swimming, right? And this would be, of course, if you pass this right here, obviously you're going to go run a whole lot more, and also you have to swim a whole lot more. So obviously past 6 you're going to increase your time. There is no way you can get a minimum here. And where did that now we can talk about it. Where did that number come from then? Well, that number that we found, which was 6 point something, that was an extraneous solution that we got. Remember, with square root for radical functions, we can get extraneous solutions. So that was an extraneous solution that we got. Okay. All right. So let's move on. Here is another problem. This problem has to do with, in this case, is optimization, but we don't get an answer as a number. So the answer that we get is in terms of a parameter. So there's a barrel that has wine in it. Let's say you want to go buy wine in a barrel, and that was actually an old problem, that people used to buy wine from a barrel like that. And then there was a little stick that you put here, and based on this length from here to here, you would pay for the barrel. Now, of course, if the barrel is long, right? If the barrel is longer, of course, the stick is going to come all the way over here and you have to pay more. But then there is a question of, should you buy a barrel that is maybe wide and short, or should you, with the same, stick, right? The length of the stick, we keep it the same. Or should you, with the same length, should you buy a barrel that is like longer and less wide, right? With the same distance, the same length. So let's say this length and this is the same. So you pay the same amount, but should you buy this or this? That's what the question is. And the answer is, well, let's see. So we're going to make this height to be h because it can change. D can change and R can change. It's a cylindrical thing, right? This is a cylinder. So what is it that we want to maximize? We want to maximize the volume, right? So what is the ratio of R and H that maximizes the volume? That means what should the ratio of the radius of the barrel and the height be so that you get the maximum amount of wine out of what? If we keep D constant. So D is not a variable, it's a temporary variable, so it's a parameter. These are the variables, right? So D is not really variable. We keep it as D because we don't know what D is, so we just give it a name. But in the problem, we don't want D to change, right? D is what we use to pay, right? So that's the same. All right, so we want to basically maximize the volume. What's the volume of a cylinder? Is the area of the base times what? Times the height. And that's what we're going to do. So let's write the objective function. So objective function is this right here, right? Is the volume. Now, of course, we have some constraint here. What is the constraint from this triangle? We have to find a relationship between D, H, and R. And again, we know that R squared plus H squared equals to D squared, right? And from here, we know R squared has to be that. So instead of R squared, we just substitute this, right? So now V is a function of only one variable, because remember, D is not a variable, D is just a parameter. We keep it. And we're going to treat it as a constant when we take the derivative. Okay, so now we have the objective function. We'll put the H over here, we can multiply it. So that's what we get. This is the objective function. And the variable of it is H. So it's a V of H. Now, what can H be? Well, H cannot be bigger than D, obviously, right? Because D here is the hypotenuse, is smaller than D. But you could imagine a barrel that is really, really wide. So H is really, really small, but R is really big, right? So it's possible for that. So we're going to take that as a possibility. So we say H can be 0, but cannot be 0. It could be close to 0 and close to D. Can be D, right? If the barrel is really, really long, then D and H would be kind of very close, right? All right, now we have the domain. So we take the derivative with respect to what? With respect to H. So what's the derivative of this thing with respect to H? We keep the pi. What's the derivative of that with respect to H? Is D squared, because that's the coefficient of H. Oh, we just put D squared minus, what's the derivative of something to the third power? 3h to the second power, right? Remember, we take the derivative with respect to h, so we don't have to take the derivative of h with respect to h, because that's 1, right? Okay, so that's the derivative. We set it equal to 0 and solve for h, right? You know how to do that? Just isolate h, right? That's a real simple algebra, right? Multiply and then isolate. You can divide by pi, you don't need pi. right? And then 3h squared goes over here, so 3h squared is going to equal to d squared. So h squared is d squared over 3, so h is d over square root of 3. We don't put plus and minus because h is positive. That's h, but we didn't want really h, we wanted the ratio of r to h, right? So what is r? R is that, and h is that. So basically what we have to do is, we have to divide them. So r, if we isolate, if we put h, right, over here in terms of d, right? So if we put d over square root of 3 here, then r squared is going to be d squared minus what? Minus h is what? H is this. I want to put d divided by square root of 3 squared, right? So now we have what? We have, this is d squared, and square root of 3 squared is 3. So it would be what? It would be d squared minus d squared over 3. Now think of this as denominator of 1. So if like denominator of this is 3, this would be 3, and this is 3. So 3d squared over 3 minus d squared over 3. So that would be 2d squared over 3, right? So that's our r squared. So r squared is going to be 2 d squared over what? Over 3. So what is r? So r is going to be square root of 2, right? D, right? Over square root of 3, right? So that's our r. This is our r. And then our h is equal to that, so we divide them. R divided by that, which is the square root of 2. That means if you want to get the most wine out of this much stick, right, then buy a barrel that has what? The ratio of radius to height to be square root of 2. That means r has to be what? Square root of 2 times h. That means buy a barrel that actually is what? Is wide, is not very tall, because see, radius is bigger than what? Than the height. How much bigger? That much. 1.4, about 1.4. So the radius has to be about 1.4 bigger than the height. So buy a barrel about like that, right? Or something like that, right? So that's the idea. And in fact, in history, there is, whether it's true or not, I'm not sure, but there is a mathematician who figured out how to buy this kind of way and get the most wine. I forgot the name of that mathematician. All right, now tangent lines and normal lines. We do one more thing here, and I'm going to end this video. So if you know how to find the tangent to a curve, but what is normal to a curve? Well, normal to a curve, let's say you have a curve. The tangent at this point, we know how to find it. Normal to the curve means the line that is perpendicular to the tangent line at that point. And that's the normal line. It has many applications. One of them I have here for you. One of the application of normal line is when you, in optics, the study of lens, right? Lenses. So here is a lens. There is a line that is perpendicular to the lens at that point. And when they talk about the rays going through lenses, and of course they break, they change direction, and that's how we have cameras, and that's how you can see actually. So this idea of normal to a surface is important in application problems. And it's important for us to be able to find the normal to a curve. And that's easy to find. All you have to find is the tangent. So what's the tangent line to x squared at 2, 4? Everybody should be able to do that quickly. So the tangent line is basically y minus f of 2, which is 4, and f prime here is 2x, f prime at 2 is 4. So that's the tangent line, right? Now, obviously, the normal would be at the same point, 2, 4, except for the radius, the slope. So what do we know about the two perpendicular lines? We know that slope of one of them is what? Negative reciprocal of the slope of the other one. Negative reciprocal, right? So that means the slope of a normal line that goes through the same point, 2 and 4, if the slope of one is 4, the slope of the other one would be 1/4, right? 1/4, but negative. So negative 1/4 x minus 2. So that's the equation of the normal line to this curve at that point. All right, so that's the end of this video. Next time we're going to talk about L'Hopital's rule. Some students call this hospital rule, but it's L'Hopital's rule. Okay, so let's end this and come back here and finish this. So I'm going to see you in the next video. Take care of yourself and others. Okay, see you next time.